In this video, I wanted to start off with the definition of what we call inverse trigonometric functions and how all those work. And let's just get right into it. So before we get into this idea, I wanted to revert back to what is an inverse function and all those topics back from chapter 2 that we described. Just to review everything, like as you can see on the slide here, it asks, are trigonometric functions one-to-one functions? So recall that a one-to-one function was a function that was not allowed to repeat its value, or it must, another way of thinking of it is it must pass the horizontal line test. Trigonometric functions are all, as we've seen with the graphs of them, none of them are one-to-one functions because they obviously repeat themselves. As you're going around the unit circle, you're going to get the same value inevitably. And why does this matter? Remember that one-to-one functions were quite important. So let me just pull back up our chapter 2 slides just so that we can review this. But remember we talked about function inverses back in chapter 2, which we often denote by the raising it to the -1 power. F to the -1 stands for an inverse function. We do the same thing with sine. So if you were to write sin to the -1 power, that would be the inverse sine function, or cosine to the -1. And when you look at your calculator, those are those inverse functions you see on the calculator button. And also other things, remember that inverse functions have the same domain and range, but they're reversed, because that's the whole goal. We're swapping x and y, and that's the whole purpose of an inverse functions. But there was one key property that was important, was that in order for a function to be invertible to have an inverse, it had to be one-to-one. And the reason is that if we're going to switch x and y and reverse the function machine, changing what goes in and out, there had to be that predictability element with a function. If we spit out a number, if we start with a number and we get an answer, we need to know, well, what caused that? Repeated answers are a problem with inverses. So that's something that this is a key problem with trigonometric functions. They are not one-to-one, which means that they are not invertible in their base form. But so how we get over this, and we discussed this a little bit with, like, for example, parabola is another example, not one-to-one because they failed the horizontal line test. We can kind of chop it in half in order to create a part that is invertible and use that for the basis. Like the square root function is the inverse, not the true inverse, but the inverse of part of the x squared function. And then the same kind of idea is applied to trigonometric inverses. But so how we might do it, and this is something in class time I might ask for you guys' like guesses on how it will work, is basically we want to take a part of the sine wave which is one-to-one that also covers the entire range. Like for example, say we were to take one period of the sine and just use from 0 to 2 pi. This would be a problem because it's still not one-to-one. We still have this double part. Or you might think about other intervals. Say, for example, 0 to pi. That's also not one-to-one. We would want a portion which is one-to-one. Like, say, for example, we were to do 0 to pi over 2. This would be a decent start because this gives me the whole range from the equilibrium to the max amplitude of the wave. But notice it doesn't pertain the negative part. And I guess I'll go ahead and just tell you, well, what is the basis for the inverse trigonometric function? The basis is, well, this kind of going through all those things I said. But basically, if we cut it out from negative pi over 2 to pi over 2. So let me use my pen here. But this is the interval of the domain of the regular sine, which we use for the basis of the arc sine. Because notice if I chop it exactly there, what we get is it attains the full range of the curve from -1 all the way up until 1. And it also is one-to-one on that particular interval. Also importantly, we also want to include quadrant 1 when we're defining our inverse trig functions, which is really important for triangles. We'll see how we use this all later. So for now, we're going to focus on the math side, the definition, all the nitty-gritty. We'll come back to how do we use this later. But this is very important for solving triangles. In chapter 5, we're going to be using these all the time. But anyways, my point is the full sine function is not one-to-one. Therefore, we must use a little piece of it for the basis of our inverse sine function. Now with the arc cosine, it's very similar, as you can see from the graph here. Also not one-to-one. Notice that if we took negative pi over 2 to pi over 2 here, though, that wouldn't be acceptable. But if we just take from 0 to pi, that is a good choice for the basis of the definition of the arc cosine, because it is 1-to-1 on the interval and it attains the full range 1 to -1. It is a little bit backwards, but essentially for the inverse functions, we're kind of pretending that's it, and our inverse function is only based on that property. So anything outside of this domain will not work. Now let me go to the packet so we can work on some examples. So all this is, I just wanted you to take notes about all of these things because they are, and also this can seem very useless and not important, but I promise that this creates a lot of annoying issues later, which if we kind of understand this, it will help later to make it all less confusing. But basically, the restricted domain of sine is from -pi/2 to pi/2, which we use as the basis of our inverse functions, and the restricted domain of cosine is 0 to pi. Now, notice this is not the normal domain. The normal domain of cosine is all real numbers because it never stops. It's going to keep going. Same with sine. Those are the wave functions keep going on forever. But in order to make it 1-to-1, we have to do this. Also, what this means is that if we're trying to figure out, well, what's the domain and range of the inverse sine functions, this is how we understand the basic. So the basic domain of the restricted sine is we're chopping it off and just using part of it. That will be the range of the inverse sine. Because remember, with an inverse function, we're always switching domain and range. Because we're switching x and y, what goes in, what comes out. And that's the whole purpose of an inverse function, is to undo what the original function does. So to undo a sine function, very difficult. That's the point of the arc sine. Oh, and forgot to mention this, it's often referred to as an arc function in the context of trigonometry. So an inverse, like if we're writing a sine inverse function, like how we normally write a sine function of x is like that. The inverse sine function would be sine to the -1. That's the way most people will write it of x. But I might sometimes refer to it as arc sine. That's just the more formal name of the function itself. It just has its own name, arc for inverse. Arc. You would also have arc cosine, arc tangent, arc cosecant. They all could have their arc functions, which is just code name for inverse. And sometimes you might see people write it out like this, arc sin, as like the abbreviated version. Most people choose to write the inverse trig functions with the -1 power. Also, reason this can be really confusing is, remember, this does not mean reciprocal of sine. This means inverse function. It's kind of like f to the -1 power does not mean 1 over f. It is not an algebraic notation. It is a function notation. So why this is often confusing is it seems like, okay, this is sine to the -1. This should be 1 over cosecant, 1 over sine, which is cosecant. But this is not the same as the cosecant function. No. Very, very different. Inverse functions are nothing at all related to all those reciprocal functions that I've been going on and on about way too much. But all these little things can be confusing, which is why I wanted to tell you guys. But also notice that for when we're taking the restricted part of sine, it does attain its full range -1-to-1, which was important because we wanted to cover the whole function and not just take as much as we possibly can. But also what that means is the domain of inverse sine is -1-to-1. And for the restricted cosine, same deal. It attained the full range of cosine, and the restricted domain was just quadrants 1 and 2 on the unit circle. And that implies that the inverse cosine will have a range of 0 to pi and a domain of -1-to-1. But all of this is important because if we're trying to understand what is an inverse function and how does it work, it's helpful to know, well, what is its domain and what is its range? Questions that I could ask you, but it's very controlled and it all makes sense based on the unit circle, and it's backwards. And if you look in the book, it will say all that information, but it doesn't. The one weakness of textbooks is often they don't get into, well, why? Why does it have these weird properties? What's the purpose? That's why, as a teacher, I'm trying to explore that idea. But also, another thing about just inverse functions in general is remember the whole purpose of an inverse function is to cancel original function or to undo. It's like if I want to undo it, or like squaring and square rooting. A square root will cancel a square. An inverse function will cancel a trigonometric function. So how this is applied to, say, an equation, say, for example, I have an equation like this, sine x equals 0.7, and I want to know, well, what the heck is the answer to this equation? What a lot of students are tempted to do is they say, okay, I'm trying to solve for x, so I'm going to divide by sine like this. But that logic makes absolutely no sense, because sine, this is not an algebraic, you're not multiplying sine by x, you're taking a function sine of x. And the key thing is that's the purpose of an inverse. Since that doesn't make any sense, the only way to cancel a sine is by using an inverse function. Any function, if you know its inverse, you can apply cancellation. Meaning that if I want to cancel out sine, I can't divide by it because it's not multiplied, but I can always take the inverse function of both sides. If I take the inverse function, like square rooting a square, or taking log of an exponential, right? Because remember, e and ln canceled each other, like, we went on and on about. It's kind of confusing, but if you know the inverses, you know they will cancel, and that will help me solve this equation exactly like that. It's sort of like I can move the sign of the other sign as an inverse. It's sort of like dividing, which is why the original notation was written as -1 power. Because it's not a normal algebraic expression, but it's algebraic in the sense of cancellation. I do personally wish they would not use that notation, because it's confusing to a lot of students, because it's kind of on a higher conceptual level. But another thing, reverting back to this, and to bring it back to a simpler point, because I'm getting kind of complicated right now, is if we think about the initial definitions of sine. Well, if I'm talking about a point on the unit circle, t is going to be the distance to that point, and determines the point, and sine always returns the y value, whereas cosine of t returns the x value. But if I'm thinking about, well, what if I know the y value and I want to know, like, let's say I was trying to solve for t, that's kind of my point. If I take the arc sine of both sides, I want to switch what's the input and output. Normally t is the input, what output is y. But if I want to input y to solve t, that's the purpose of the inverse function, to undo what goes in and what goes out. And same with the arc cosine. If I plug in x into it, it will tell me where am I. So it's the exact opposite procedure. Instead of giving me where am I at in terms of t and giving me x, the arc sine and arc cosine will take where your x and y point and return to you, well, what is your position, assuming it's in the proper domain and range, of course. Let's in the next video, I'm going to do a few examples of evaluating these and actually putting this into action, because I think that will help you see a little bit more about how these actually work. Because the definitions are, there's a lot going on. See you in the next video.